through the microphone? Cool. All right, we'll get started. Thank you for coming. I bought chocolate because it's my last day. I'm sad. Thank you for being great students. I really enjoy getting the opportunity to do this. So this is my thank you for turning up. And notice a couple of long blinks on these 5 to 7 ones. So keep yourself awake with sugar. It's probably not the healthiest thing, but we'll give it a go. Okay, yeah. So as I said, last one for me, I hope. Otherwise, I'll have to pad like crazy tomorrow. But I think, yeah, no, you got Claire coming in tomorrow. Last one for me, end of Unit 4. Big homework coming up. Is everyone stressed or everyone just cruising? You're cruising? Yeah, everyone attack this guy then for help. No, if you've got any questions, ask me in the break if there's enough. I can pad a bit at the end with that stuff if you're interested in that, or I can do some random things to show you some interesting stuff. Cool. So, end of Unit 4. Okay, we got into doing a bit of basic stuff. Not so interesting. Talking about floating point and floating point representation. So we've only got 64 bits. How do we represent the whole real number line? This thing called floating point. Not super, I'm not myself, like I don't know what Yoni's going to do in the quiz, but it's not so much about the representation. The take-home point for when you go to do this stuff for real is like, I think in your head, it's evenly spaced between powers of 2. That's the one I always remember, which is kind of interesting. That's how they decided to get the dynamic range. And also this floating point epsilon problem where you've always got this little bit of semi-stochastic fluff every time you do a calculation in floating point. So you're never going to expect it to be exactly on. Every time you do a calculation, there's going to be this little bit of, it ends up being like probabilistic sort of reasoning you end up doing when you're doing numerical stuff in floating point. You're always going to have this little extra bit of stuff coming along for the ride. And if you do some silly stuff, it can compound. Yeah, so yeah. So again, those floating point epsilons, if you do enough of this stuff, you end up you can just kind of recite them. Should put the camera on. Didn't do that today. Sorry. Yeah, if you do it enough, you just end up memorizing those basically. The 10 to the minus 16 for float 64s. If you see something down around there, you go, oh yeah, it's floating point. Not too much of a worry. Okay, numerical inaccuracy issues. This is my favorite, that we lose associativity. I think this is the most interesting one to come across. Like you would usually expect it to not matter where you put the brackets, but with floating point it does, but it depends on the numbers. This is just, again, you're going to get this 10 to the minus 16 little bit of fluff. Don't get too worried about it. Just know that it's going to happen. So things that you would expect to happen, you're going to, if you're putting asserts in your code, like you're doing testing, if you're going to put equals equals, you're going to be sad. You're always going to have this approximately equal. And you can set up really pathological numerical schemes. It's a thing to keep in mind. And we're going to, I guess, for mathematicians or mathematicians in training, the first time we're going to run into this is when we take numerical derivatives. So I think we talked about this like when we're talking about motivating doing Newton's method, that basically this is another one of these cases, like just using the definition, what you'd learn is the basic definition. The only difference between this approximation and the definition is you don't have a limit there for h, that you can use this to approximate a derivative, any derivative you're interested in. Funny thing is though, naively, you would assume that, like in mathematics, limit as h goes to 0, this thing gets more and more exact. In floating point, no, not so lucky because of this stuff we were just talking about. So we're going to set up, I might as well just copy some of this stuff across because why not? So Julia. So we've got a little thing here, optional named argument for step size. We're going to have f, takes in a function f, takes in a value x, and all it's going to do is default to square root epsilon for the basic one, and it's just this definition again. So f of x plus h minus f of x divided by h. So if we have some random function sin x, Sorry, who can tell what I did wrong there? I didn't do an inline function by doing that. If we want to go diff forward, my func. So what's the derivative of sine at 0? Who can actually do calculus? Who's 1? Everyone agree? So hopefully we get 1. So that's cool. That looks like it's doing the right thing. We change h something big. Let's go ludicrously big. Diff forward, that's a terrible approximation to h. So you'd expect as you go down, should get better and better. And then as you get better. So from this side, the calculus side, you go, oh, as you come down, sailing down from this side, from big H down to small h, it's getting better and better and better and closer to the true derivative. However, we've got some funny function here. We've got some 2 ones. So funny one, in the notes, we've gone for sine squared x. I don't think there's any particular reason for this function. What we're going to do, we know, you guys can tell me if this is true. Do you believe that as the actual expression for the derivative for sine x squared? Who's super confident? Yeah, you're all more confident than I would be. Cool. So that's the true derivative. What we're going to do is we're going to take a step range in powers for this one. So we're going to go from a really, really small number, 10 to the minus 14, steps of 0.1 up to the minus 2. So there we go, 1,200 of these guys. Basically just broadcast this through at one point. We're doing it at 2 different points in this one. So if you look at this one, we'll just interrogate. So it's taking the absolute error, what's relative error, absolute relative error. I don't know what the naming is going to be a little bit awkward for this guy. Basically, do this forward difference approximation, do the analytic expression, divide it by the analytic expression at that point for all those different step sizes. So x naught, I didn't seed, that was these guys. So put it here. So we're going to do it at 2 different points. This is kind of interesting to show that analysis in this case is going to let us down. So that's that one. Just reproduce the rest. You get what the plot's doing. There's not much interesting to say. And we'll just kind of eyeball it. Yeah. So we've plotted on a log scale down the bottom. That's this y-axis log with the symbol log, x-axis equals log. That's if you want to do one of these log-log plots, just to see how it's scaling. As we come in from a high value, this is exactly what we were talking about before. You know, errors are monotonically decreasing as we reduce the step size. You notice at a certain point, though, it starts to go absolutely bonkers. Errors start to increase. And this is basically the floating points cancellation stuff we were talking about. This one in particular here, I was saying, if you've got a big number plus a little number and how addition in floating point will work, kind of gets absorbed. I think I showed you, let's see what I had in my notes. Oh yeah, down there somewhere. So quickly, it's worth rereading this one. You know, addition is just subtracting the negative, so the same logic works. If you want to add 2 floating point numbers, basic way to think about how it works is you shift the exponents to the same thing and then add them together or subtract them. So because this is going to be like the decimal equivalent of a bit shift, it's going to push the little bits off the side when you make them bigger. So this little one, if I went up, if this was 10 to the minus 7, say, I would be basically having nothing left of this expression. So that's what's happening as we do this down in this side. We've got this funky floating point error starting to dominate. And it's not nice like the calculus side. The calculus side's like this linear, nicely decreasing error. When you get to the floating point side, it's kind of jagged and jumps around and hard to actually reason about where it's going to be good and bad. What a nightmare. And interestingly enough, you do it at x equals 0.5 or x equals 5, and you get a different minima for where the error is minimized as well. So it's not like a thing where this gets a little, as I was saying, gets a bit stochastic and gets a bit like hand wavy. lot of this floating point stuff is like error tolerances. You can bound it, but actually reasoning about where's the best spot, like what would you choose for your step size, it's kind of like, try it and see. It's really unsatisfying, but that's what you get. Hope that's clear. Numerical derivatives. It's probably confusing. I would say same logic applies if you're going to do any higher order derivatives. So if you're going to do like partial derivatives, if you're going to do something like a Jacobian, I think that's, everyone happy if I say Jacobian, what I mean? No, cool. I won't say too much about it. Basically exactly the same logic where you just go, if I want to approximate the partial derivative, you just take a step in each coordinate one at a time. So if it was a function of x, y, z, you just go x plus h, do the difference, y plus h, do the difference, z plus h, do the difference. Make sense? Just hand wavy? Cool. That's actually a nightmare though, because that scales badly. We've talked when we did sorting, we talked about, orders of like, what's a good order for a problem? What's a bad order for a problem? In my day job, I'm doing optimization on very large problems. This is like, I think the one I was doing today, not today, yes, on Friday, my n in this case would have been a variable with like 2 million parameters. So if I was going to do finite differences in 2 million parameters to work out something like a gradient, I'd have to take a step in each one of these one at a time. So if my function evaluation is a little bit expensive, which it was, you can imagine that doing finite differences one at a time through all those things to work out which way is downhill, if I'm going to try and optimize something, that's kind of going to be bad news. So just show you this is kind of like cutting to the end. That the reason I can't do derivatives anymore is because I'm lazy. There's this thing called automatic differentiation. Has anyone heard of this before? No? You should it's like amazing when you first learn about it. So this has been around since the 60s, but only gotten really popular with neural network libraries coming popular. So basically every neural network, has anyone played with neural networks before? What have you used to do it? TensorFlow? Anyone else? Anything weird? PyTorch? Yep, PyTorch. Basically, those two libraries are these huge projects. Torch comes from actually a Lua. It's called PyTorch because it was in Lua first, strangely enough. So if anyone's played Roblox and done scripting in that's Lua. So you might know Lua or not know it. But the original neural network library was in Lua, and then they converted it to Python. So that's why it's PyTorch. They're just front ends for automatic differentiation engines. So what they're trying to do is like when you're doing a neural network, you're going to go like, I've got this super rubbery function and I'm trying to fit it to data and I've got all these magic numbers I need to fit. I need to tune all those magic numbers to give me a good answer on the fit. So you need to know the sensitivity of the loss function to the weights of the neural network. So you can think of every one of these huge projects as just a front end to an automatic differentiation library. So the way that's gone, if you go back to it, you probably use JAX is the one people use now, which is a bit more like this library called Zygote. Oh, it's not happy. Do a little bit of pre-compilation because I messed something up. But I'll just wait for that to finish in the background. Basically, yeah, so this thing is like, it's a super normal problem to do something like a Jacobian. Jacobian's one number, you got one number, like a function and giving you one answer. So that's like, if you're doing optimization, you're going, this is good, this is bad. Given the numbers, try and minimize the sensitivity or go downhill so you get the minimum loss. Just waiting for this while it spins its wheels. Sorry, everyone. Yeah, not uncommon for these ends to get absolutely gigantic for modern problems. So I guess depending on what field you're interested in, you're saying economics. If you're doing economics, economic problems do get massive, like trying to optimize massive problems. It's like in industry, super normal case of doing things with thousands to millions to billions of parameters. Neural networks are kind of the extreme example at the moment where it is scaling to billions of parameters. So anything like finite differences is actually not feasible. Cool, I got that. I managed to talk while that was doing that. And this is why I can't do calculus. My brain is utterly broken because I'm lazy and I can just do this. So what this will do is through type magic, I've just defined an anonymous function here that's going like x and y goes to 3x plus 4y plus 1. And I want to evaluate the gradient at 0, 0. Because Julia, warm up takes the first time. This will give you the analytic derivative to floating point error for this function. So by a magic process called automatic differentiation. How it actually works is very complicated. I'd encourage you to go off and read it. But it's basically this, there's different modes, blah, blah, blah. I'd encourage you to go off and read about this yourself. But the basic concept is this algebraic structure called a dual number. And you can imagine if you're doing something like the chain rule in calculus, if you have a number that's got like, what did they say? It's form A plus B epsilon, and every time you get an epsilon squared, you drop it away. You can kind of automatically do the chain rule. So if you know the derivatives of base functions and then you compose all these functions together, you can kind of, if you track through that computation graph, you can cancel out all the epsilon squareds and then get an answer for what the actual derivative is analytically. Kind of magic. I encourage you to go off and read it. It's a huge, huge thing. So any function you'd want to do, you just have to give it 3 numbers if you do that, blah, blah, blah. Like magic, absolute magic, amazing. I wished I'd known that, would have saved me years. I literally spent 1 month verifying by hand that I'd done the correct derivative to a problem I was doing once in software with finite differences because it was for an important problem. So I had this thing and I was trying to propagate an error through it. So I needed to know the derivative because I think I made this joke before, applied mathematicians have only got one trick. It's like do a Taylor series and cancel it at one term, make it a linear problem. From trying to propagate errors, I needed to do this thing and it was worth it that it took me a month or so just doing finite differences and verifying hundreds of different cases and then putting that in a test case for a thing we were doing. So I don't have to do that anymore. So all that filed in the bin. I don't know how to do derivatives anymore. Magic. Cool. That's automatic differentiation. That's a cool thing. What do I say? This is kind of interesting though. You probably would have noticed this, Jewel. If I say like, what's easier, differentiation or integration? Which one's easier? Differentiation? Integration sucks, right? Like it's kind of like you have all these weird ad hoc methods and they don't kind of work sometimes and lots of stuff to remember. Flip the case. Integration numerically is really easy. Differentiation's hard. Like this automatic differentiation library is kind of really sophisticated. Numerical integration schemes are kind of dumb and they just work. The dumber the better, which is what I plan on showing you today. So yeah, integration's super useful. My life is probability. I think I've, again, trying to motivate this stuff. Usually I'm doing something like one of these Bayesian problems. So like, I'll go like, in my day job, I have some data about a scan of a mine face. That's what I do in my day job. So I have all these different types of information and I go like, cool, what's the probability that this is mineral X, like say hematite, given this data? Cool. Bayes' theorem flips that around and goes, what's all the different ways you could have got this data if it was hematite? Prior probability of hematite divided by all the different ways you could have got that data. And that bottom line is kind of the killer because it's like you're integrating over all these different variables and that can be huge. So interesting problem is like, not so much this univariate one, but multivariate one. We'll go to that in the end. But that's actually the tricky bit is like where this scales to huge dimensions really, really quickly in probability, like all the time. Yeah, I mean, again, we did this earlier on when we were talking about factorial. You can use the definition, the undergrad, the first definition. Has anyone done any measure theory yet? You have? Can you explain Lebesgue measure in one sentence? Nobody can. Yeah. So like first definition you'll learn is Riemann sum. There's other definitions of what integration means. I'll just put that out there. But you don't usually, this easy one of like, we just cut it up into boxes and we sum up the boxes, then we make the boxes small. That's like the basic way to think about integration, and that kind of works amazingly. Question I would ask is like, what would you do to make it? Has anyone done a numerical integration course? I should ask first, so you know if you already know the answer. Have you done any courses on this stuff yet? Anyone? All right, cool. You get to free form. How would you make a better approximation? What's like something dumb you could do? Trapezoids? Yep. What next? What's better than a trapezoid? You can always make smaller boxes, yeah. What sort of function approximation? Yeah. Yep, that's right. So you can go basically all the schemes that are the higher order integration methods are basically fitting higher order polynomials to the data. So like if you've got, but problem with this is you're gonna have a strong assumption about the smoothness of the function before you do this. Because like if you've got a wonky function that's like really jaggedy, it's not gonna be a great idea to do that. But for smooth functions, if you know something about your problem, you can go just fit higher and higher order splines through the data, higher and higher order polynomials, and you'll get a much better estimation of the integral. That's what these basic intuition for all the higher order integration methods are. So the first one would be, as you said, good answer was, you know, just draw a line, and then, you know, you draw a wiggly line. There's like, you know, you could add more dots so it fits up better and better, and just sum those up. So every higher order integration method is this. And back to my first lecture, I was saying, you know, this difference engine that Charles Babbage was inventing, that was for doing this problem. It was for interpolating polynomial coefficients. That's what it was for. So that's where historical background for that stuff is that. Turning through the crank of this simple method for estimating finite width. Yeah, basically every higher order method is just an interpolating polynomial of higher order. You do a higher order method, you get more. This family are called the Newton-Cotes formulas. I think these were kind of drilled into me when I was in your position. We had a whole course on this stuff. Basically, though, I'd say that's the intuition, though, that you can go, you know, the trapezoid rule, Simpson's 3/8 rule, Boole's rule. And you can say something about how the error term shrinks with H as you go up. And you see that like third order, fifth order, seventh power, you know, so it shrinks really, really quickly. Cool. You know, you could even imagine, you know, like you could come up with your own higher order method if you wanted to. And there's books full of this stuff because that's what people used to do in the old days. Like you could imagine I'm going to do a 128th order polynomial and see what the answer is. Cool. Yeah. The form you get if you propagate that through is something like this, blah, blah, blah. Okay. I think this is my time to talk about special cases though. So we'll follow through this one. So we're going to look at special functions. We've got some funky little function that does, what does this guy do? So we've got Riemann sum, FAB method defaults to midpoint, and it returns this. If it's Simpson's, it's this higher order method. So basically what we're going to do is we're going to have a little switch function. You can give it a method. It'll go between, are you going to use the midpoint rule or are you going to use Simpson's rule? Just to see what the difference in errors are between these two. I've got two weird functions here, or not too weird. We've got x 10 to the cos x, f1, and f2 is just exponential x. So two functions, we're going to investigate what their error characteristics are like. As you said, derivatives are hard and I don't like doing them anymore. Integrals are even worse. So we won't talk about that. But trust me, this is like, trust me, bro, on this one, that the integral for this f1 is this thing called a Bessel function of type I, order 0, 10. You had a Bessel function for question 2. Yeah, they come up. Anyone come across Bessel functions before this? Basically, if you do any like mathematical physics. It's when you have cylindrical symmetry. So the one I always think about is like a drop in a puddle. That shape is like a Bessel function when you have that circular symmetry. They're the kind of functions you'll get out with that boundary condition. But just trust me on this one that this F1, if you do the integral from 0 to 2 pi, you'll get this guy, integral from the other one. So similarly to the derivative one, some oracle gave us the answer of what the integral is. What we're going to do is just go through a range. I'll just talk to the plots though. For this one, you guys can follow this. I don't think there's anything super special here. If we did, again, different dx's, so different spacings, what does the error do for these two functions? So I think I labeled these really badly. So kind of in your mind, ignore the right-hand side plot because that's kind of chumping to the case. This one is the exponential one, and this does exactly what you would expect analytically, where you go like, oh, using a higher order method, the errors are going to be smaller. Simpson's error stomps on the midpoint one, right? Second case is kind of bizarre though, because like if you look at these ones, is there any difference between these two? So effectively, no. So there's a lot of caveats with this stuff. Like, what's the point I want to make here? It's not so simple to work out. Like you can do this asymptotic analysis, but the special case matters. What matters in particular for this function is that we have a smooth periodic function. So I've got a periodic function inside an envelope. What you can actually show is that for smooth periodic functions, midpoint has great error characteristics. So like you don't need to do any of these higher order ones. The dumbest one works really, really well. And I think maybe the intuition is with if it's periodic, if it's, you know, if you've got the rectangle on one side or the other side, it's going to kind of cancel out. So for smooth periodic functions, this is what happens. Has anyone heard of the fast Fourier transform? Does that come up? Yeah. Why do you know it? Yeah, you can do it for that. That's definitely one application of it. Do you know? Yep. Yeah. So you can think of like a Fourier transform as decomposing. You can think of it. It is. I think it is what it is. You can decompose it into a sum of sinusoids. If you had discretized the Fourier transform, you would naively have an n squared algorithm. And trust me, magic algorithm fast Fourier transform is n log n. But funny thing, this always came up to me is like, oh, but they only ever do like they do the dumb one. They do like the midpoint rule for the integral. Like the approximation for the integral is just rectangles when they're doing a fast Fourier transform. And that's because you're doing audio processing, smooth periodic functions, usually for audio. So this thing has great error characteristics. So it's enough to do that. Things you might not have known, but like this has huge applications. So like if you go off and do numerical methods for PDEs, you'll hear about spectral methods and things like that. You're probably less familiar application of fast Fourier transform would be JPEG. Everyone's heard of a JPEG? JPEG uses discrete cosine transform to compress the data. That's kind of crazy. See if it gives us a nice JPEG artifact. Yeah, that's a cool one. This JPEGy blocky artifacts that you get for low quality compression, you get like, I don't know what else you would have seen that has, I don't know if I should have preempted this one and come up with some examples, but JPEG works in little blocks doing discrete cosine transforms to make it sparse, which is something we'll talk about at the end of this lecture, but that's application of fast Fourier transform. Okay, high dimensional integration though. High dimensional, this is one I care about. When I'm doing a problem, I'm doing integrals over thousands of variables. Oh no. So what do you do then? So what would be your intuition for how you would approach a n-dimensional problem? So say we're doing an integral in 2D instead of 1D. What would you do? Yeah. Yep. And so would you do boxes or would you do triangles or how would you cut up the domain? Simplex, yeah. So some simple little shape. So if you try and do higher dimensional integration, they tend to be called cubature methods. I have no idea why. It's one of these wonky old historical words. They call it cubature. Yeah, they actually scale incredibly badly. We've got an example of that here, and I'll show it. We've got this funky function, f of x equals 2 times pi, blah, 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 blah. But x is a vector. So we've got like this inner product form talking about last lecture. We're going to do this H cubature and see what the error characteristics looks like as we get bigger. This method is kind of clever. So what it does is it does basically like some sort of simplexy, partition-y thing, if you can imagine that in your mind in 10 dimensions of like cutting up the space into little blocks and fitting surfaces. This library will do that, but it will give you an estimate of its own error. We kind of watch what it's doing as we get up to 4, 5. Oh no, it's starting to go very wrong. 8, 9, 10. It's by the time you get up here, it's kind of like its own internal estimate of its error is terrible. Isn't that interesting? Anyone got a better idea of how to do higher dimensional integration? Sorry? It's more about when you go up into high dimensional spaces, everything's kind of far apart. So the idea of a simplex and like, what is that thing is kind of like, what's going on? So that's why these things tend to fall apart a bit. Has anyone got a different idea? You could do cuts. You could try, is that what you mean? Like something like that? Okay, I'll take the state of the art for this thing. I'll show you guys. I don't know what the polite way to say this is, but I'll go here. So let's take a really simple problem. If we're going to go, here's a circle in a square. I'm going to take a dot. Let's see if I can select a dot. So everyone can do, pretend the circle's an easy case, right? So we're just making it easy for ourselves. Circle's the thing we're trying to find the integral of. What's the integral of a square? Can everyone do that in high dimensions? That's easy, right? Easy-ish, right? You can just cut it because it's lined with the dimensions. So what we're going to do is we're going to kind of throw shit at a wall and see what sticks. We'll just take a random point and go, is it inside the shape or outside the shape? Yeah, that's exactly right. We go inside the shape, outside the shape, count up. So you just need a test of inside or outside, and we throw a random point, throw a random point, throw a random point, count the ratio. That's the ratio of the areas. Done. State of the art. Believe it or not. I got one here. High dimensional integration. Cool. So sorry, this isn't in the notes. This is just me playing around. We're going to use, okay, just a bunch of functions. We've got special functions, plots, H cubature, linear algebra, random. We're going to do exactly this case. We're going to do the volume of an n ball in n dimensions. So I don't know what you call that. Is that the right word? That'll do. Another one of these ones of trust me, this is the analytic expression for the volume as you go up in dimensions. If any of you are really excited and motivated, you can go and tell me whether this integral is correct or not. But it has this funny gamma function thing we were talking about before. Who remembers what that is? Yeah. Yeah, it's like the real extension of the factorial thing. So this, again, trust me, I wouldn't trust me. I'd go off and verify for myself, or if I was lazy, I wouldn't. We're going to do this. So this is a really simple thing. We're going to uniformly draw random points in n space and see if it's less than r. So this test is really simple for this shape. That's kind of a thing I've dodged. You just have to check whether the norm is smaller than the radius. That's the test. Really simple. Going to go for I equals 1 to n samples. If the norm of this random thing uniformly randomly distributed in n dimensions, just draw a point in n dimensions. If that's less than r, I'm going to increment the inside the ball divided by the number of samples and volume ratio. That's all that function does. I've got some cubature thing where I had to do something funky and split it in half. Don't worry too much about that. Cool, I'll just run this. I think it's cool to just run the whole thing. Okay, so maybe so doing this sphere, this is one that blinds my head. Like I love maths because I have terrible intuition and you think about these high dimensional objects and I kind of have zero intuition. So I love it. I love it when my intuition breaks. So this one is super surprising to me. Oh, sorry. Can't get my mouse is playing up on me. Oh, you pain in the bum. Just got to get that corner to drag it to make it big. Okay. So surprising thing to me is I wouldn't have expected this, but I've got this volume ratio and it's actually going up as you go up. And it's like, how does the ball fit in the box? It changes with dimension. And by the time you get up to 10 dimensions, the ball takes up nearly none of the box. Is that obvious to anyone else? Does that make sense or not make sense? The kind of like, my only kind of like grasping for intuition would be like, if you think about like, they're getting longer and longer in the corners as you go up into dimension, and most of it's filling out in that space. So the ball, by the time you get up to 10 dimensions, 15 dimensions, hardly any of the points land inside the ball. You might, if you do a million trials, you might only get one inside the box, in the ball for the box. All the rest are falling inside the box. Maths is awesome. That's why I'm not a pure mathematician. I can't think that big. But what we see here is if we do the I've tried to be fair, and I've set this up. This is on my test repo if you want to go and look it up after the lecture. Try to be fair and give them the same sort of compute budget, so it runs in the lecture in like a minute, give them the same number of things. But what you can see is that this thing of like just throw stuff and see if it's inside or outside, that actually scales really well. So the difference between these two, like pretty subjectively just looking at it, it's doing pretty well. We could just give it a bit more compute budget. Whereas this thing just loses the plot at like 4 or 5 dimensions. It's absolutely useless. This idea of partitioning the space and doing clever surfaces dies. So 2 or 3 dimensions, these methods are superior. Plotting how it scales with dimension, this relative absolute error, again, this guy flogs it. This guy is losing the plot completely. So state-of-the-art method, I think we were talking about like sorting, and you can come up with these pathological random algorithms for sorting that are bad. Sometimes random algorithms are awesome though. Monte Carlo in this case, later in the course, you were doing a thing called Markov chain Monte Carlo, which is like the algorithm of the 20th century. It's like the everything algorithm. You got a problem, you can solve it with MCMC as long as you're willing to wait long enough. Kind of answers every maths problem. The people who invented it were kind of excited because it's like, oh, this is the end. We came up with the thing that does everything. But not quite true. There's a bit more to it than that. Has anyone come across MCMC, another course? You have? Yeah, super powerful method. But that's an indicator. This is like your first hint of like a Monte Carlo method, randomized algorithms actually winning. I think it's awesome. Okay, back to the notes. Differential equations. So cannot understate the importance to all of the rest of science. You guys are in the pure bit of maths, like everyone else is a subset of you guys. For everyone else, differential equations are like huge part of the sciences. Like most of physics is just mucking around with differential equations. Engineering is the same. So all these incredibly sophisticated software packages for simulating differential equations. FEM, if you've ever heard of that comes up, finite element modeling. Like if someone's going to design a car, they will design it in software on an FEM package and then verify it before they even make anything. And then when they make it, they basically trust that it's going to work. That's the kind of where the world is at the moment. Not so much with fluid dynamics. So there's like a place for mathematicians still. We haven't sorted out everything yet. Partial differential equations are an utter nightmare for numerical methods. ODEs are nice. So no PDEs in this course. Generally, so one example of this is like, we were talking about like, what would you expect as you decrease the step size for the numerical derivative? It's like until you get to the floating point bit, you would expect the error to reduce, right? For ordinary differential equations, same logic applies. If you decrease the mesh size, the solution should approach the analytic solution. When you're in PDE land, you can have all these funny things going on where if the ratio between the step sizes is wrong, it will converge nicely to the wrong solution. So it's not even consistent with the maths. So it's a whole thing. Much more approachable. We're only worrying about initial value problems here. Differential equations, and I saw on EdSTEM someone had a problem. Did anyone have a problem installing differential equations? It's a huge library these days. Doing homework? Everyone fine using it? Did it take a while to install? It's massive. It's actually, I would say, the best of these differential equation libraries going around at the moment, particularly for stochastic differential equations. There were some methods invented by the main author of differential equations that didn't exist before, which is kind of exciting for me. Spring mass damper. This is like a physics thing, but it's in a maths class. Sorry, everyone. If I say this, I drew a picture of it just so you guys can get a handle on it. Okay. So have you had to do this stuff in maths course on differential equations yet? Not really. Do you do application stuff or is it just talking about differential equations? So spring mass damper you're pretty happy with? You are, at least. Everyone else? Yeah, I'll go through it anyway. So do it with the engineering notation. Imagine you've got like, this is my really terrible drawing of a spring. And this is like a fixed support and a mass under the spring and this thing called a dash pot because it looks a bit like what you would have if anyone rides a mountain bike and you look at the front fork, basically one of those filled with oil, and air though for one of those. It's actually the spring and the damper at the same time, but anyway. If you imagine some coil spring, you've got a mass. If you let it go, it'll go jigger, jigger, jigger at an equilibrium spot. If you poke it, you expect it to do this kind of damp sinusoidal thing. The damper is actually like physically a piston filled with oil is what they have in real life with holes in it. So as it pushes, you get a force that resists the motion. The spring's like a restoring force from a position. So this guy has a force that's a function of velocity. This guy has a force that's a function of displacement. That's the modeling bit of it. Tried to write that down over the side, just so when we go over to the other bit. So you'd say force, bit of physics, force equals mass times acceleration. The restoring force from the spring is like minus some spring stiffness times x, and then the damping is some constant times v. In real life, this real world is much more complicated than this. This is like the dumbest model of this stuff you would do. The spring one is actually pretty good though. If you get a spring and actually measure what its force versus displacement relationship is like, till you're bending it, it is actually really linear. The damping is actually incredibly nonlinear for real systems. So in a car, the damping going down is much higher than the damping going up, like 3 times higher down. So it's actually an incredibly complicated nonlinear system in real life, but we all lie to you when you're undergrads and say, oh, it's just a constant. So we're going to say acceleration with a bit of notation. Acceleration is the second derivative of x with respect to time. V is the first derivative of x with respect to time. So if we put all that together, we'll end up with something like m times second derivative of x plus cx plus kx equals 0. That's like the starting equation. If we write that out as a system, this one always did my head in when I was an undergrad. I can remember clicking on this when I was coming with this. Like, to write it as a system, you're basically just using the definition for one and then substitute in for the other one. So like x dashed equals v. That's just the definition. We haven't, the full expression, the more interesting one is this one, where if we go like v dashed equals x double dashed, and then we substitute in. So this x dashed is v minus c on m v minus k on m blah. If we're writing that out as a function, we could do this. I'm sorry, this is a bit terrible. It didn't come through. Imagine this is a vector in this case, where big X is a vector. So I'm writing this as a system, these two guys lumped together. It's some function of this vector X and t. In this case, the function of t is really boring because it's just a non-autonomous system. It just doesn't depend on time at all. So in this, just being super explicit, x equals little x and v as a vector. And F is a matrix where it's 0, 1. If you look at this one up here, there's no term that depends on X in that first bit, but there is a constant of 1 times V. That's that second term there. Down the bottom line, though, we've got minus Km for X in the first spot and minus C on M for the second spot. That's where the system comes from. Pretty straightforward. Linear system in this case. They're nice, but real world's not that nice to us. That's where we start with the notes. So using differential equations, linear algebra, and plots, we've got some values for these coefficients in the notes. Sorry, I called it C. In the notes, it's B. It's fine. Don't worry too much. This matrix should be just exactly what I said, I hope, or I've lied to you all. Just basically that thing again. That's where that funny thing comes from. This is an initial value problem. So the problem with all this stuff is you need to start with an initial state. And then what this discretization tells you is what to do with the next step, one time step ahead. So you can start from an initial spot, propagate it through this matrix, go, this is what the next spot's going to be. That's how these guys go. Simulating for a T range, the manual solution, you know, if you guys have all done your differential equations course, you can probably solve for this, some exponential function of that system matrix, T multiplied by the initial state. So that's the manual solution. I'd pay attention to this little funny API. So linear right-hand side. I kind of feel like there's a funny API everyone's landed on for solving ODE problems. So it's good to pay attention to it, how they do it, how you pass the function in. Pass in the system, pass in your initial state, pass in a time range. So clever methods will adapt the time steps for you. How they do this is kind of sophisticated. I don't know what you need A for. Anyway, yeah, there's some plots. So you can see if we do it in terms of this, if I say phase space, is anyone going to go like, what's the phase space? Yep. Basically those system variables, X and V, right? Like this is displacement and V. So that's kind of, some people call it state space, some people call it phase space. I don't know what the name should be, but just how the state evolves with time removed as a shape. That's what we're looking at here. So in terms of displacement, it's this spiral down into the equilibrium position from the initial. So this would be the start one. And implicitly time is running around here. And if you plot it versus time, the thing is you can't really plot displacement and velocity. You kind of can, but you have to fiddle with the scales. You'd have to, that's harder to plot. So if we look at displacement versus time, it's got this damped sinusoidal thing, time running this way. You guys can play around with animations to make that look cool. So super sophisticated method. How does it work? They're really similar to numerical integration. They kind of look superficially similar, but they're harder to think about, I guess, because you kind of like, you know, anti-differentiation is integration. You can kind of think about it that way. It's probably not a helpful way to think about it, really, but just for these ones, there's a superficial similarity between these two. The dumbest way you can do it is to do this approximation that they've constantly been doing, where you just go, I'm going to pick a step size in time, and I'm going to go, this is my discretization in time, and I'm going to do this to come up with a recursive algorithm that says, for the next time step, I'm my previous time step plus the time step and the function evaluated at the previous state. That's called Euler's method. Make sense? So basically, you're just going to take this guy for the, so we've got our system of equations. That's that thing we were writing out here. We've got a system of equations. This x dashed equals f of x, y, blah, blah. Annoyingly, I've changed the definition y. Y is x in my previous one. This can be a vector of solutions. And basically, if you plug this into here and rearrange, you'll end up with an equation like this. Hopefully, you can all do that and see that. That's how this thing works. So it requires, because this recursive, you've got this recursive definition, you need a starting guess. It's an initial value problem. So you need to give it a first, where am I starting from, and then march forward in time. Cool? I'm not going to belabor this too much, but there's higher order methods that are very similar to this idea of doing the higher order integration, where you're going to go, I'm going to use intermediate steps to kind of guess what I should do. And there's certain magic choices of stuff that cancel out errors. So they're Runge-Kutta methods. So superficially, I look at that and I look at something like the Newton-Cotes formulas and I go like, oh yeah, it kind of looks like one of those guys, like that one, you know. They kind of got the same logic to them when you go through the derivation. So there's this kind of one-to-one between these guys. And this is kind of this similar idea that you have an intermediate step. I've thrown you for a loop though in the notes. Has anyone gotten up to question 15 and 16? Yeah. I introduced something called a symplectic integrator. So this is a really interesting case of what the point of doing this method should be is that worse is better in this case, that if you know something special about your problem, there's something better you can be doing for that particular problem. In this case, symplectic integrators, I don't know how much I said in the question, but they can be shown to preserve something like the energy of the real system. So there's this idea of, there's a lot of guff. I think I'll actually talk about it because I think I throw lots of people when I do this one. Yeah, a lot of guff. So where's the meat in this one? So this is like when you're working in the real world, there's like a lot of information and most of it's crap. There's just a little bit of gold in there. The two little bits of gold for a hint is like, here's a system of differential equations you can write out, basically like we did before. That's appropriate for something like Euler's method. Here's a system of second order differential equations that are appropriate for something like a symplectic integrator. So if you're going to do it, you just need to write this guy out as a system and this guy out as a system. So stuff about Hamiltonian systems, really basically, if you can write it out as a system of second order differential equations, you can just plug it into one of these symplectic integrator methods. This is a very, very simple, it's like a two-step thing that's almost the same as Euler's method. So in terms of computational complexity, it's actually kind of modest, right? Like you're not doing much more than Euler's method, but because it's preserving energy, the long-term behavior of this thing is much, much better. Because the solution will always be close to the true solution. Yeah, leapfrog. Okay, what do I want to say about that? Okay. Has anyone done any like dynamics, like classical dynamics? Is that a thing people do anymore? No. Do you know about planetary motion? If I've got like a sun and one thing around it, there's a family of solutions that are famous. I think it was like one of the Bernoullis who came up with this, of like, what's the family of solutions we would expect to see? Does anyone know? Sorry? Conic sections, that's the one I wanted to hear. Yeah, ellipses are one bit of it. So probably find a cool picture on Google Images. That's the one I want to show. So if you've got a two-body problem, you can do a reduced two-body problem in every case. So I just kind of went, one of them's bigger than the other mass, so you can just pretend it's one thing going around the other. But it actually works every two. It doesn't depend on the mass. They're actually rotating around their center of mass. And every solution, if you want to do the cool, like beautiful maths version of this, it's conic sections. Every solution, there is an analytic answer for, and it's one of these. It's like, it's either a circle or an ellipse, and then you've got these unbounded solutions where it just kind of wings in and goes off to infinity, where if it's hyperbolic or parabolic trajectories, they're the family of solutions. So in the homework, if we're comparing it to, you could actually compare it to the analytic solution if you're really excited. I wouldn't expect anybody to do that, like for the two-body problem. What's everyone's expectation of what that's going to happen to that when we add more bodies? What's going to happen? Does anyone read Chinese science fiction or watch Netflix? Three-body problem, infamous. Book's good. If you haven't read it, read the books. They're fun. Yeah, what's famous about three-body problem or n-body problem? Chaotic, yeah. So just because I like to suffer for you guys, I did a four-body problem with a symplectic integrator for this guy. And I started 4 off in a non-equilibrium steady state. And this is what happens if you have a four-body problem. And you get crazy stuff going on. Close this guy, so that's a bit bigger. So this meant to motivate, like, I don't know how good everyone maths is, but what's the equation for crazy snakes? Like, you could not write out an analytic solution for this. Conic sections for 2D totally can do that. Increase the problem difficulty just a tiny bit more, and you get something that's chaotic. And so like a 3-body problem or 4-body problem, it's hard to do any analysis at all. Basically, all you can do is equilibrium states. But if you look at this, you could get intuition about stuff that's happening for more complicated problems that can give you some more insight into the actual problem. One of the things I noticed with this is you see they're starting and they actually start pulsing, right? They're actually becoming unstable by like something like a sinusoidal solution, and that sinusoid grows to a certain critical threshold and it breaks off into crazy town. That's something that if you didn't have computers, how the hell would you ever know that that might be going on? And when I was an undergrad in your spot, everyone was super excited by chaos theory. Now everyone's just kind of like, hey, it's a thing. Don't worry too hard. But I think I seeded this question to you guys of like, how do you generate random numbers on a computer? Is there a deterministic process to leading to something like random results? Here's a mathematical deterministic process that's extremely sensitive to initial conditions. So if I give it exactly the same initial conditions, it would do exactly the same thing. But with things like floating point, which was how chaotic systems were discovered in the 60s, was someone they weren't using floating point, they were using fixed precision initial value problems, and they had 6, and then they tried to start it again the next day with 4, and they got a different answer, and they're like, what the hell's going on? Months later of debugging, they're like, oh, it's actually something about nonlinear dynamics we didn't understand before, that seemingly simple systems can generate surprisingly complicated results. And so maybe this is a method for generating random numbers. If I capture this far enough apart in time in state space, they're uncorrelated enough with each other that they're basically random. It's probably not efficient. If you're sophisticated enough, though, you would look at this and you'd go, Paul, I don't believe that's real. I think that's floating point. And I'd go like, I can't actually prove to you that that's not an artifact of floating point, because none of us can do the analysis hard enough to actually prove that these things are actually going on. So mysteries of mathematics. Question about, so here's I'll go start with an interesting fact that you can, as I was saying, this thing seems like it's got some exponential growth of trajectories. The solar system has that. Anyone want to guess what that number is for, like how long apart in time before you can't predict what the solar system is going to do? 15 million years. So not long time. We're all not going to be dead, but that's okay. But not that long. And like it's again, one of these things, they've only shown this with numerical experiments. They can't prove it, but they can show with numerical experiments that it looks like you go far enough in the future, we can't actually predict where anything's going to be. And another question that's kind of interesting, because you're all thinking about computational complexity. If I have an n-body problem, if I think of the force of gravity between things, how does that scale as the problem grows? Not exponential, it's not that horrible. Not cubic. Sorry, squared. Squared's right. So everything attracts to everything else. So you have to consider the positions of everything. So if you go to the astronomy department and they've done a simulation of a galaxy for celestial dynamics, I don't know how many stars are in a galaxy, but have they really done a simulation of that? Can you do n squared for however many billions of stars are in a galaxy? Yeah. So fun stuff. I think there was like algorithms of the 20th century. Another one is something called fast multipole methods. So if you go off and try and do this stuff for real, I'll do all these symplectic integrators with fast multipole methods for how you turn that scaling from n squared down to n log n. Cool. I'll take a break now because that was an hour. Yeah, there's chocolates. Go. Knock us about.
Last lecture?
Yeah. Differential equations. Oh no. They're not building codes. Like, just try again and again. Because it's manually building something like sometimes it'll give you a warning that you didn't finish compiling. You can trigger a compilation. Like package compile. Yeah. Sorry.
How do we use it? So,
Yep.
But then when I try to run what question tells us to run, it brings this up and then
yeah, okay. So it's starting a server. So what it does is basically a server starts and runs all the time. You need to poke messages at it from another place. Yeah. So you can do this from Julia, would be the way I would do it, where you do a HTTP post. So I can give you an example of that. I'm showing you requests in the notes, but I haven't shown a post. That's what you need to do. You can try it.
Yeah.
I would look at so maybe I remember my first error before it even looks like was yeah, so no, it'd be like what you're doing basically run it with a model.
Yeah.
And then
so this is it running with model just in the background.
Yep. And then you have to send this down. I have issues with the last day. I haven't looked at this documentation.
Oh, you have to, it like breaks something. Whereas they have to solve it like every month.
This stuff can be posted.
So you generate the vector, put it in, just like solve it.
You can put that in Julia. That's pretty straightforward. What you'll do something in Julia would be something like using HTTP contact.
It's the same. It's basically the same resolution.
Sorry, you do something like HTTP
adjust the sub, right?
HTTP.post. If you look up this guy, it will take a URL. This will be running on a thing called localhost on your computer. That's in the notes. It'll say 127 blah 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 blah. That's just like the web address to a server running on a computer.
Yeah.
And then the bit that's tricky if you do it from Julia is you actually probably need something in the header, which will be. I actually got one of the tutors with this. Just try it from curl first.
Yeah.
Would be my advice, and then maybe I'll post something. Curl is just like for sending a web request.
Oh,
it's like a yeah. That you'll need something like that in there. Post URL content type blah blah application JSON X, and the dictionary would be something that's like this. Model messages. Yep.
JSON, but the key is you have to like kind of back convert in the string into the dictionary and then get JSON, pass it, and then get that out. Are you doing it wrong? Or is it like it's gonna be?
I do enjoy it. It's not that bad.
Oh, speaking of
Yeah.
like make a program, and it says in their notebook like put it like say put a screen cap like say calculation.
Okay.
And like that, do we also include script or is?
I'll tell you myself. I don't know. This question to ask one of the tutors because I'll be asked, but that would be how I read it. Yeah. Okay. Also, or send a message on anything and see, check the market. That's what I do.
Okay. Oh. All right. I don't actually have heaps to go, so this is good. And I can just show you some random stuff after this. Okay. Everyone happy? Good. I didn't mute this. No, I'm still good. Okay. So again, applied mathematician. All I can do is do a Taylor series and turn it into linear algebra. Linear algebra is the most powerful thing in mathematics for applications. If I had a chance to do my undergrad again, I would have spent more time learning linear algebra. I've learned so much more outside than I did in my undergrad. So it's so useful. And useful, maybe I'm old though, don't take advice from old people, but everything will change. Yeah, if you think, would Python be as popular for numerical stuff if NumPy didn't exist? No, and NumPy's kind of terrible because it's like all this deep in to do matrix stuff. It's kind of nice for it to be standing up. It's like something that, as I said, like MATLAB was literally invented as a matrix calculator. So that's the whole point of it. So it's such a useful thing to be able to do. The range and scope of what you can do for analysis grows so much when you can turn it into a linear problem, because like all the smart people have thought about linear problems and done everything you can do. If you can familiarize yourself with all the things you can do in linear algebra, you'll be in a really good spot. Okay, linear equations, factoring matrices in various ways. I think I'll start with motivating this a better way. Question 14, did everyone have fun or not so fun? What's that? Haven't done it. Has anyone done question 14? No? What's that? Looks fun. Yeah, so let's motivate it this way. If I told you that question 14 is a $1 trillion algorithm, would you believe me? So the original version of Google's search engine is basically this Markov chain thing. So how do you sort web pages based on hyperlinks? Is like, they managed to take a problem, turn it into a thing in linear algebra, do linear algebra stuff and make heaps of money. There you go. So maybe if you don't find linear algebra fun, you might find money fun and you can go chasing lots of money. If anyone hasn't seen that, I think it's good to talk through. This is just pure motivation for linear algebra question 15. So it's really simple. We're going to go back to the 90s when I was young, when there were 3 web pages. I don't know how many web pages there are now, but it's a big number. So this problem was, this is this thing of translating. You can try and take a problem in the real world, translate it into a maths problem. Basically, websites have links to other websites, and you could represent that as a directed graph where you're going to go like, if I link to you, I'm going to have an arrow that points to you. If you link to me, same the other way. So basically, you're trying to work out which of these web pages is the most important, right? That was the whole point, what they were trying to do back in the day. So like the idea was all these things are associated with this query. Which one's the most important? Then I give that one at the top of the list, and then I get people to pay to be further up the list, and that's how I make $1 trillion. Cool. All the search engines before Google sucked, like at that time. There's like a big jump forward in the performance of these things, and people were manually curating them and doing all sorts of crazy things. So just for, I don't know how maybe it's a bit political, but it's actually while they were doing a master's project or a PhD project at uni, they did it too, and it was all government funded. And then they went off and started a company off that, and they made all the money. So it's kind of interesting how this stuff works. So yeah, literally the algorithm is called PageRank for Larry Page because it was his. Yeah, yeah, so we've got a digraph that's going like directed graph, if I say digraph, directed graph going like I link to you, B's linking to C, C's linking back to B, C's linking to A. What's a model for how someone in the 90s browsed the internet? Randomly clicking links with a certain probability. So that's where the Markov chain comes in. So the way they set up the algorithm was, I'm going to randomly jump to each hyperlink, and I've got some random probability of teleporting. And so if you set this up, it actually is equivalent, directly equivalent to this Markov chain problem in question 14, where you're going to go like, what's the stationary distribution? That stationary distribution is the page rank. Cool. Thinking about how things scale, there's more than 3 web pages on the internet. Could you make that structured pi matrix for the internet? How big is that going to be? Even worse, how big is the vector going to be for P? You can't even fit that in memory on a single computer. So all the clever stuff is there. But anyway, that's just meant to be a motivation for why you should care about linear algebra. I care about it for various reasons, doing eigenvalues, linear matrix solves, all that stuff. Julia will basically do everything. Kind of annoyed that you have to include linear algebra always. So the syntax for a matrix is kind of gross. I think I showed it here. Okay, so we got, you do spaces for the stuff on the same row, and then to go down one, you do the semicolon. So I haven't said what K and B are, but you know, 1, 2, 3, 4. That'll make a matrix A. Ooh. You should never, until you've done a bit of linear algebra, you should not know that the inverse function exists, the inverse of a matrix. You never, basically never, ever want to calculate the inverse of most matrices. You want to multiply by some factorization of the inverse. That's, if you take nothing else away, but you can calculate an inverse. Why would calculating an inverse be bad? What's that? Yeah. So you might have an arbitrarily small determinant, and taking the inverse might be a really bad idea for all these floating point reasons I said. So cool. You can do matrix multiplication. I didn't say what B was, so that's going to be problematic. No, I don't have it in my command history. But this one's clever. Uniform scaling. So this is kind of a clever optimization. If you're going to do an identity matrix, what are most of the values going to be? 0. So like, why would you bother making that matrix ever? So this comes into this idea of sparsity that I'm going to talk about in the last little bit, maybe, if you're interested. You can make a uniform scaling object that will scale everything, and this thing never actually allocates. That's the clever thing with this uniform scaling. So if I'm going to have, doesn't have to be an identity matrix. You could scale everything by 2, scale everything by 3. That's this uniform scaling thing. So if I do uniform scaling 2 times A, if I make a different A, so this is what's interesting about this is this guy, let's call it Q. I can do Q times, not that Q, Q times A. If I make B equals 1, 2, 3, 4, 5, 6, 7, 8, 9, I can do B times Q, and it still works. So it doesn't actually have a size, so you can actually do this uniform scaling every time. Useful, because you're going to waste a lot of memory if you allocate that thing for no reason. This, it'd be surprising if this was true. So this is a thing of like, taking the inverse is a numerically unstable operation. You just kind of have to take my word for it. Proving it is hard. Just like the determinant might be arbitrarily small. You probably get out something, like we said, floating point, every time you see this 10 to the minus 16, but this can get really, really bad. If the determinant's small, this will get really, really bad really, really quickly. Cool. This guy is the magic algorithm though. So slash going the wrong way. Is everyone familiar with this from MATLAB? Or, yep, seen this before? So this is, if I do this, like help, this will give an indication that it's left, give floating points results, blah, blah, blah. So if it's scalars, it's kind of boring, right? But this guy is kind of a hint. It's like matrix division using a poly algorithm. So anyone heard of a poly algorithm before? Poly algorithm is an algorithm of algorithms. So it's an algorithm that decides which algorithm I'm going to actually apply depending on the attributes of A. Underneath, this guy is incredibly sophisticated. It's choosing which type of factorization do I do. I'm going to do a matrix solve on this thing based on the properties of A. So examples with dispatch, it's kind of like dispatch you could think of, but a bit more explicit. It's like if I was a symmetric matrix versus a square matrix versus a matrix of complex entries, you know, you might do different things in each of those cases. Very, very sophisticated, more sophisticated than me, and it's smarter than I am. So like I think I know a bit about linear algebra. I default to this unless I'm trying really, really hard to be clever and fast. So when it says using like do a matrix solve, I think one of the questions in the homework says that, you know, basically you're trying to set it up to do a matrix solve. Cool. We showed this stuff before where we've got using general linear models to set up a linear model and solving an overdetermined problem. Like this is like a typical regression problem where you're going to go like, got lots of data, I'm going to try and summarize it as a line. What's the thing that minimizes the sum of squared residuals? You can do all that, or you can do it by hand. So minimizing the sum of squares is what you do. We've got two coefficients here. We've got, for a linear one, you've got a beta naught, beta 1 times x. And you want to minimize the difference between the fitted coefficients for the line and the data. You can set this up as a matrix problem. That's what you kind of try and do. And yeah, it's kind of funny that way, stated that way. Yeah, so this is the thing called a Vandermonde matrix where, sorry, going a little bit fast. A would be a matrix of the data. It's an n by 2 matrix in this case where it's just got ones and seconds. We'll show you this. I'll just do it. I think that's the one. X vowels. I jumped to the end too quick. I got to run that to get the data, but anyway, I can generate this myself. Let's make it more fun. We'll do more. 10 y vowels equals 2 dot times x vowels plus 3 plus. So I'm going to take some random data on a uniform interval. That's the x vowels. Going to add a little bit of fluff. We'll see if it's an appropriate amount of fluff. Oh, didn't like that. We need broadcasting everywhere just to be safe. Cool. So if I go plot, so maybe scatter, x vowels. Yay. Cool. I think we want more noise than that. That seems like too easy. Let's bump up the noise to 1. Okay, so we've got some noisy-ish data, and we're going to try and find the trend line through these two, and we're going to want to solve for the coefficients. So in this one, I explicitly stated that this is the secret data is 2 and 3 for the slope and the offset. The way you would do this, set this up as a matrix problem by hand. We would go set up this thing called a Vandermonde matrix. if you're going to do a squared problem, like a quadratic problem or a cubic problem, it's just like more of these. You just go x vowels squared up to the order of the whatever polynomial we were going to solve for, but we're just doing linear. So A looks like this. And then hopefully you could see that how would we actually solve for these guys? So if we did A times 2, 3, did I get the shape right? There we go. So let's just see what I did. Scatter, x vowels. So we know what the answer is. So I've just put the solution vector 2, 3 in there. Hopefully I got that the right way around. We'll see pretty shortly. Plot. Did I get it the right way around? No, I did not. That was guaranteed to happen. Q equals 3, 2. There's the good Q through there. So got a linear approximation. We know what the answer is. The question is, how do we get that solution vector back out of this from the data? That's what we're doing. So in the notes, we've given you like a zoo of methods. Yeah, basically every different way you might want to do it, but this, I'd say like, do it this way. This is this one, like I was saying, this is this poly algorithm where it decides what to do for you. Where it's giving me basically, plus or minus whatever estimation error I've got, it's going to say it's 3 and 2. So you're taking the matrix, just to be clear, I've said like Q equals A times this. So if I'm going to try and solve for the inverse, I'm going to A matrix solve Y values to do the least squares solution. But as an indication of what might be going on underneath, you can form the normal equations and solve this. This will be more numerically stable. If I do A dash times A, what's going to be the properties of that matrix? What's it going to happen to it? Got any idea? Square matrix and symmetric is the other one. So like this diagonal term, because I've done this A dash times A, it'll be a symmetric matrix. And it's smaller. So A itself, so depending on the shape of A, doing this like in a producty type thing would reduce the dimension, make it much more stable to invert. And if you know that this is symmetric, you can do different methods. That's where all these other ones come in for. I'm not going to go through them all. Under the hood, what will actually be happening most likely is it will do something called a QR decomposition. That's like the generic case for this stuff, is a special factorization of the matrix where, what do we got? So you've got this guy's F has 2 bits. It's got a Q matrix of some funny type, and then it's got R, which is an orthogonal matrix. So R times F dot R. Oh, wrong way around. Anyway, you get the picture. That's like, that makes the normal equations anyway. So whole zoo of methods. You could be clever and try and do this yourself. You can do a singular value decomposition. You can do something like gradient descent. They should all give you basically the same answer. But my teaching point would be don't. In the first instance, use the clever thing unless you're trying to be fast. So in this current job, I have had to be super careful, super clever to make things fast enough. So I work in a place called Plot Logic, got on my drink bottle. We do scanning for mining, hyperspectral scanning. So special camera, each of our data cubes we capture. So it's like a picture, normal picture, but each pixel has 500 color channels within it. And all the information about what's inside that pixel is happening in that deep color channel information. So really like lots and lots of data. So I need to be super fast with some of the algorithms we're applying to it so it can happen in a reasonable amount of time. and need to do tricks. So I've spent a lot of time mucking around with optimizing special factorizations to try and make stuff quick when I'm doing it. Say biggest one is the biggest optimization you've got a hint about so far is this thing called sparsity. And this is, again, I put this in here because came up when I was out in the wild. No one had ever talked to me about it. And it's this really obvious thing of like, we talked about, I think I've tried to deliberately say, if you do this, if we do this guy, it's not making a vector, it's making a thing called an iterator, does a unit range. If this gets really big, I'm going to start allocating an unnecessary amount of memory. Don't need to do that. I just need to make a thing that will give me the next value. I talked about here, this uniform scaling. If I have a big matrix, like say it's like 10,000 by 10,000, and I need to, my identity matrix is a bad example, but just say I need to multiply it by an identity matrix. I really don't want two things that size hanging around in memory, because I'll quickly run out of memory. I'll have nothing left on my computer. So this is another example where we're kind of exploiting this idea of sparsity, where we don't necessarily want to make the thing where we kind of know what's happening because it's just full of zeros. Yeah, it's kind of more interesting than that. Really super useful dealing with large sparse matrix. So the idea is that you only keep the non-zero elements of the matrix and their index. So rather than going like, I'm going to make a matrix where I'm going like A goes to 1, let's make it interesting, 0, 1, 0, 0. I could just make it something like a dictionary, really, that goes like index 1, ind I goes to 1. Oh, sorry. Let's pretend it's ij. Anyway, 1, ind j equals 2, value equals, like. So I'm going to make a dictionary, basically a dictionary that goes like, this is the indices of all the non-zero values. And then I'm going to make the methods clever to do things like matrix multiplication or matrix sols. Then I'm never, ever going to have to allocate all this memory for stuff I don't ever actually need. So luckily, oh, didn't say what they were. They're just strings, string. Anyway, blah, blah, blah. It's already built in for me, so I don't need to think about that. Sparse matrices are everywhere, though. When you're doing mathematical modeling, basically everything you're going to make is going to be a sparse matrix. You're never going to have these things like, if you're thinking about a physical simulation of something like we did this spring mass damper thing, how often is it that I move something over here and something at the other end of the universe has to worry about what's going on here? I mean, it was true for the planetary motion one, but maybe not quite. So this thing of like having long range effects is usually not the case. Usually things talk to each other through a system, they propagate through, and that propagation through the system is usually local. It's really local. So an example would be, didn't talk about this, but I'll just do it here quickly. If I've got something like a second derivative with respect to some variable, the approximation for that is going to be x at, I'll just do it as Julia, k plus 1 minus 2x k plus k x k plus 1. So this is like, if you do the, that approximation twice, you'll end up with something like the x squared. So, okay, you get the picture. That as a system is all on the diagonal. You're just going to have a matrix that's just got like something down the diagonal and two things down the side. Everything else will be 0. So things like if you're doing partial differential equations, say, it's typical that your matrices that you'll be doing it as a system for will be super sparse. They'll just have this little bit of structure. You can think about it like if we had a mechanical system, we go back to this springy thing, if we've got like, say we were simulating this desk, one thing we could do is we could decompose it into a little bunch of springs and masses all attached to each other, and they're only attached by their local connection. So you kind of get this sparsity naturally. The only time you'd get a long-range connection was if somehow a spring attached from here over to the other end. But even then, that's still sparse, and everything's not talking to everything. That's not the normal case. So maybe for if you've got a statistics band, inverse covariance matrices in the real world are nearly always sparse. You don't have things that have the correlations between things. Like if you just looked at the covariance matrix, yeah, it's dense, but magically the inverse covariance matrix is actually really well approximated by something that's not dense. Super common. Basically, you could think about, I realize I'm kind of waffling here. Oh, that's not what I wanted. Yeah, these systems of interactions like Markov chains and that, similarly, like we were talking about, like how big does a matrix have to be? It doesn't have to be that big. Average website has a bounded number of hyperlinks, or you could probably only worry about the top 100 and chuck the rest in the bin. Problem is actually much, 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 much smaller. So that's this idea of sparsity in terms of dealing with this. I got a really simple example of this here. So you've got to use it as modules, sparse arrays, RPack. There's some funny things. So like the linear algebra methods won't work straight out of the box for doing these things. Like if you want to solve for, say, like the eigenvalues of something, if you try and use the linear algebra eigenvalues on a sparse matrix, it's not going to know what to do with them. So you have to include some special stuff. This is a stupid example of a social network. Say you had 10,000 people and you're going to try and make a friendship matrix. You go like, for every person, am I friends with you? Not going to make it symmetric because the world doesn't work like that, unfortunately. You can be friends with someone, they can totally not be friends with you. You can not know. That's a thing that happens. This is basically making, so as I was saying, if you're going to make a big dictionary, the way you would do it is you're going to go like, I'm going to find out the row values and the column values where there's a value. So I'm going to set this matrix up and go like, if they're friends, you get a 1, not necessarily a symmetric matrix. So 10,000. And I'm going to do the dense version of this and pray that my computer has enough memory. Pretty sure it's fine. Just going through randomly simulating, if there's some tolerance, you get this kind of funny animation. Big zero. So I'm going to make the sparse version of this. The sparse constructor is you give it the rows, the columns, and the values. Because I'm not doing anything interesting, there's no strength of friendship. It's just 1 if you're friends or not. You'll get this big matrix. So the interesting thing is big zeros. If you want to know how big this guy is in memory, we can do this var info friend matrix. This guy is only 15 megabytes. So 10,000 by 10,000 by float 64, you probably wouldn't do a float 64 unless you were going to do, this is a tricky thing though, you might want to float 64 if you're going to do something like eigenvalues or matrix solves on this stuff. This is only 15 megabytes. Anyone want to guess without looking about how big just a thing that big full of nothing is? Yeah. So it's 800 meg of basically nothing. Yeah. So the actual information in this thing is tiny. It's like 15 meg. And you can store this sparse representation. Then if you want to do something like this, you can go like, this is a challenge for you guys because I'm not going to do it in the lecture. I can do the eigenvalues of this sparse representation. This comes up all the time. If you're trying to do clustering, you're trying to work out like, here's a clique or something, like all these people are friends, doing more of this linear algebra stuff. Working out connectivity of graphs. So it only takes 2 seconds to do this. Is like, if I do Eigs, random, I'm not actually sure how this scales. If I did 1,000 by 1,000, which is like, I've gone to 10,000 by 10,000 with this one. Oh, I didn't do time. That's not very helpful, is it? Yeah, 0.7. So how this thing scales. If I do 2000 by 2000, that's probably going to be about the same time as the big one, or worse. Worse. It's much worse. Yeah, 6 seconds. So this thing, you know, there's special methods built in to deal with sparsity. Cool. Yeah, don't even try and take eigenvalues of a dense matrix because this thing scales like order 2.4-ish. We talked about that before. So it's somewhere between order 2 and order 3. Order 2 would be amazing. That's just reading in the values of the matrix. Order 3 would be doing the naive thing. It's dominated by some matrix multiply somewhere. So this thing scales like matrix multiplication. Yeah, dense matrix. So cool. That's where it's kind of interesting is like you start thinking about like if you had one of these giant systems, how do you do an eigenvalue decomposition? You can't store the matrix in memory. How do you do it? And it ends up being some funny thing, like all those different versions of question 14 where you go like, do it with linear algebra, do it by solving for the stationary distribution, do it with an eigenvalue thing. There's iterative methods for doing this stuff to make them scale even better as well. That's stuff to have fun with later on. I just thought I'd show it to you. Now, I guess I've got a little bit more time, so I will. It's called fun with linear algebra. I don't know. That's like a big claim, right? Might not be fun. Let's do something totally weird with linear algebra. I'm going to use it to compress an image. That's what this point of this demo is. I'll do it. Start a session here, actually. We'll just do it in here. Terminal, new terminal. Julia. Okay. So images, that's my day job. And images get really big really, really quickly. So I don't know, what's the resolution on your smartphone now? Like 20 megapixels? I don't even know anymore. It's not like people are keeping track. That's like a lot of pixels. Like they're getting really big. I got an image here. I'll load this image. Oh, not so happy. So there's some special stuff with types of images. This is kind of a hint about what's going on. You go images, normal images, not the ones I deal with in my day job, have 3 color channels, a red, a green, and a blue. That's to cover most people's vision. Both my boys are colorblind, so they don't need 2 of those. Actually, surprisingly little information across color channels in normal images because they're so blobbed together. If you look at the spectrum of how people's visual response reacts to images, there's kind of like a lot of overlap anyway. It's kind of surprising. So it's got a special 8-bit type. So each one of these is an 8-bit number. So 8 bits, how many levels do we get? 255, 256? Yep. Yep. So someone decided people can't see changes in intensity that much in images. So you only get 255 values. You only get 3 colors. That's enough. People won't notice. That's the standard for all these images. So if you have something like, I've loaded in a JPEG, but if you have a raw image, it's an array of 8 bits, one for red, one for green, one for blue, and sometimes this thing called an alpha channel, which is kind of like, don't worry about that though. That's just confusing. Okay, that's the big image. I'm going to, just to make this analysis easy, I'm going to resize it down to 1/4 the size to deal with it because size, image, big. That's a photo off my phone from a couple of years ago. It's already 3000 by 4000 pixels. It's kind of big, right? Like if that thing was in memory, as it was, it's kind of a big thing. Like, I don't know if any of you noticed, like what's the size of a normal image from on your phone? You probably don't worry too much because memories, like phones have a lot of memory now, but like, it's not that big though. It's not hundreds of megabytes each image. So something magical is going on. I sort of said something about fast Fourier transforms before, but we're going to do a dumber version of that. So I'm going to cut the color channels out. I'm using the images package. Channels, channel view, blah. Just so you can see what I'm doing. just making a bunch of matrices for each color channel. So what I'm going to do here is this thing called a low rank approximation. Singular value decomposition came up before. It's kind of not the best way to think about it, but has anyone done PCA? Has that come up in your education so far? You have? Principal component analysis?
Yeah, in econometrics. Yeah.
Econometrics. Could you give the 5-second summary of PCA?
You create new variables that summarize the features of a few of the others.
Yeah, it's a bit tricky, right? Like I always think about it as you're trying to find. Let's just get an image. This is the like 2D version of PCA, right? Like you've got some ellipse in space and you're trying to find a rotation that will align the big axis with one of the axes and the small axis. And you'd say that big one is the principal axis. So most of the data is going this way, this way. Lots of different ways you can actually solve for this. SVD is one way to solve for this rotation that rotates the data so that the information is kind of aligned with one axis. So what I'm doing here is something funny where when you do an SVD, let's just do it. So I'm splitting out each of these color channels. Okay. This thing. You got these three bits. You've got a U, an S, and a V. So a U will be a orthonormal matrix. So it's like this kind of like this funny rotation thing. Then you're going to have the S matrix is a bunch of scale factors. That's how you scale it. And then the other one is unrotating it back into the original frame. So interesting thing about this is if we plot the singular values, it's kind of a boring plot, but bear with me. Where'd it go? Don't know where the plot went. Disappeared on me. There we go. So you notice as you increase the number of, as you go up in these singular values, the first one's really big and then they get really small really, really quickly. And I won't show it here, but interesting thing, color information is not that interesting. They're usually quite correlated with each other, reds and greens and blues. They all kind of move together. You don't actually get that much information from color. So like when you're doing machine vision and stuff, a lot of them work in grayscale because the color channels don't really give you that much. That's what we're trying to do. Notice the thing is that these things decay really, really quickly. Okay, so recall, I'll say that maybe this is optimistic, but there's this thing called the trace norm identity. This is, if I consider this, has anyone heard of the Frobenius norm? Has that come up before? Frobenius norm of a matrix? How would you say, like intuition-wise, if you've got a matrix, how would you say how big it is? Like a norm. What could you do? What's a dumb thing you could do? You could just, like I think you said it, just pretend it's a big vector, sum of squares. That's the Frobenius norm. So you can say the Frobenius norm of a matrix is equal to the square root of the sum of the singular values squared. So if our singular values, which is this S thing we're plotted and they're dropping off really, really quickly, you can actually reconstruct the original thing with a few of these original singular values. You don't need them all because they're dropping to zero really, really quickly. So if we decide to go like, we're going to threshold these guys, pretend they're zero, reconstruct it, we're going to end up with a thing that's much, much smaller than the original matrix. Cool. If you don't believe me on that guy, you can just verify yourself. So they all approximately, what's going on with this guy? Yep, so approximately true, given some floating point stuff, that the norm of the channels is the norm of the SVD S values. So sum of singular values get the same thing. So what we can do, that's what this guy here's doing. If you look at this, when we reconstruct it, we're going to take this U matrix to K terms. We're going to take the first K singular values and we're going to take the next K of this V matrix and use that to reconstruct the original matrix. So it's going to be much, much smaller. It's just an outer product. they're kind of like eigenvalue-ish. It's like for non-square systems, like you can go like, it's the SVD to eigenvalue thing is kind of, there's a thing there. You can do PCA by doing from eigenvalues, or you can do it from SVD. They're two equivalent ones. Looking at how you would calculate it between those two methods would probably give you the intuition you want. I'll just do this guy. What the approximation error would look like. So if we go like, what's the sum of the reconstructed stuff? This is going to some funny window I don't like. So if I include one singular value, what this plot's saying is I get like, I'm only 20% off in Frobenius norm from the original one. So if I just took one row vector, one column vector, did an outer product of those two, it's only 20% off in error in Frobenius norm. And this thing decreases. So as I start adding more and more terms, the error decreases, gets down to 0. So by the time we get up to like 70 singular values out of the 700 or so we had, you basically reconstructed the original image. So most of the image is junk. Like most of the image is like noise that we don't care about. What does it look like? We'll do this. So we're going to do each of the channels independently. And I'll do all these plots and we'll see what it looks like. Let's run through it. Sorry. Oh, it's already done. Here we go. So this is a photo, a random photo, but I invite you to take the code and play with it yourself. This is this first one where we've just done an outer product between two vectors. So everything's kind of streaky, right? Like, because we've done an outer product. It's just two vectors. We add like 20, 40, 60, 80, 100, starts to look like the actual image. So interesting thing, perceptually though, this is kind of jarring, right? Like we've just done it as outer products and people go like, it doesn't actually look like how I think about images. So we're putting some induced sparsity on this thing to do the approximation. We're going to go like, oh yeah, that looks right. In terms of perceptual metrics, it's not winning so well, but it's an interesting thing, right? Like it's an interesting hint about how you might be doing this thing. So yeah, it's an interesting question. Again, I talked about compression and randomness and stuff like that of like, if you are going to consider images and how many possible values they could have, if you've got, each color channel's got 255 values, there's 3 of them, 1,000 by 1,000 image. The space of possible images is massive, right? Like if you're trying to think about all those images that could possibly exist, the space of interesting images, you know, what images that people could interpret is like this tiny thing up in the corner. So like this is this, we don't have machine learning in this course, but I think it's an interesting thing of like, you know, the actual information content in things is much smaller. Trick is finding where it lives. And it's not through a linear method. So this is just a linear method. Nonlinear ones, you could probably get a lot better. Okay. Yeah, so the size of this guy compared to the big one, 1e to the 6, this guy would be 36 megabytes compared to 700 or something. So we get this massive reduction in size if we did 1% reconstruction error. Encourage you to go off and read though, because if I go to the source code here, Paul Silly test repo, and you look at my test image, how big is it going to be? This is the full size image, 3 megabytes. So perceptually lossless, JPEG's an algorithm from alien technology. Like it's 10 times smaller than this funny thing we did. The trick's putting it in a space where it is much faster. I'd encourage you to go off and read about that because it's well beyond the scope of this course, but super interesting. Okay, and that's me done, I would say, in terms of the course content. Yeah. Oh, I got a gift.
Oh, you brought gifts.
I bought chocolates, yeah.
Is it through this?
Yeah, sorry. I'll pass it over.
Thanks. It's not at the end of every lecture series that somebody gets a gift, but just Paul now has done 4 years of this course, and that's about 400 students. And really, thanks so much. It's not something that people from industry like Paul come and do, you know, to make that extra little summer vacation payment, but rather the passion, and I'm sure the class felt it and the students before. The gift is because maybe next year Paul's on a break, but we'll see. 2025 is a wild card. So can we please have a round of applause for Paul? Thank you. Just some alcohol and sugar.
Okay.
No. Okay, and tomorrow we'll meet Claire just here at 6. And thanks again, Paul.
No worries. Thank you, guys.